technological know-how.
Technology has played a big role in developing the agricultural industry. Today, it is possible to grow crops in a desert by use of agricultural biotechnology. With this technology, plants have been engineered to survive in drought conditions. Through genetic engineering, scientists have managed to introduce traits into existing genes with a goal of making crops resistant to droughts and pests. Every farmer uses this technology in their own way. Some use it to create fertilizers, others use it to market their products, and others use it in production. For years, scientific and technological advancements have benefited farmers in the industrialized world by driving agriculture production. However, smallholder farmers who are responsible for 80% of the food in the developing world have yet to see similar gains. These farmers, the majority of whom are women, lack access to many of the tools needed to be successful, such as modern irrigation practices, crop management products, fertilizers, post-harvest loss solutions, improved seeds, mobile technology, as well as access to information and extension services. Through these tools and through much greater investment in agriculture, we can move toward more sustainably curbing global hunger and malnutrition around the world by dramatically increasing productivity yields, conserving food by substantially reducing post-harvest losses and food wastage, giving farmers access to real-time information and services in the field, and even improving the nutritional content of foods. In this lesson, let us explore how technology is put to use in agriculture from the following headings. Use of technology in agriculture, major trends in Asian agriculture and technology development, integrated pest management, no-till or conservation agriculture, agricultural technology in India.
Use of technology in agriculture. Use of machines on farms. Now, a farmer can cultivate on more than 2 acres of land with less labor. The use of planters and harvesters makes the process so easy. In agriculture, time and production are so important. You have to plant in time, harvest in time, and deliver to stores in time. Modern agricultural technology allows a small number of people to grow vast quantities of food and fiber in the shortest period of time. Modern transportation. This helps in making products available on markets in time from the farm. With modern transportation, consumers in Dubai will consume fresh carrot from Africa within the same day that carrot leaves the garden in Africa. Modern transportation technology facilities help farmers easily transport fertilizers or other farm products to their farms, and it also speeds the supply of agricultural products from farms to the markets where consumers get them on a daily basis. Cooling facilities. These are used by farmers to deliver tomatoes and other perishable crops to keep them fresh as they transport them to the market. These cooling facilities are installed in food transportation trucks, so crops like tomatoes will stay fresh upon delivery. This is a win-win situation for both the consumers of these agricultural products and the farmers. The consumer gets these products while still fresh, and the farmer will sell all their products because the demand will be high. Genetically produced plants like potatoes can resist disease and pests, which rewards the farmer with good yields and saves them time. These crops grow very fast, they produce healthy yields. Since they are resistant to most diseases and pests, the farmer will spend less money on pesticides, which in turn increases on their return on investment. Development of animal feeds. This has solved the problem of grass to feed animals. Now, these feeds can be manufactured and consumed by animals. The price of these feed is fair so that a low-income farmer can afford them. Most of these manufactured animal feeds have extra nutrition which improve on the animal's health, and the output of these animals will also increase. In agriculture, the health of an animal will determine its output. Poorly fed animals are always unhealthy and they produce very little results in form of milk, meat or fur. Breeding of animals which are resistant to diseases. Most of these genetically produced animals will produce more milk or fur compared to normal animals. This benefits the farmer because their production will be high. Crossbreeding is very good in animal grazing. Crossbreed animals are more strong and productive. Irrigation of plants. In dry areas like deserts, farmers have embraced technology to irrigate their crops. A good example is in Egypt, where farmers use water pumps to collect water from River Nile to their crops. Most of these farmers grow rice, which needs a lot of water, so they manage to grow this rice using irrigation methods enhanced by advanced technology. Advanced water sprinklers are being used to irrigate big farms, and this helps the crops to get enough water, which is essential in their growth. Some farmers mix nutrients in this water, which also improves the growth of these crops. Major trends in Asian agriculture and technology development. The Asia-Pacific region has been on the forefront of generation and transfer of modern agricultural technologies, recording the highest agricultural production growth rate, about 4% during the past 2 decades. The Green Revolution ushered in through the development and adoption of HYVs of rice and wheat more than doubled the productivity of these crops. Besides, advances in soil and water management, integrated pest management, post-harvest handling, and other related disciplines have synergistically contributed to the increased productivity. Similar developments have been recorded in the livestock and fisheries sectors. The region is also using modern biotechnologies to produce genetically modified plants, animals, and microbes, resulting in superior quality products, increased productivity, and resistance to biotic and abiotic stresses. However, the above gains were linked with negative influences. The Green Revolution technology has generally bypassed rain-fed dry land areas and resource-poor farmers, thus exacerbating inequity. Production of some of the poor man's crops, which is pulses, coarse grains, roots, and tubers, remained stagnant or even declined. The irrigation-associated problems of salinization and waterlogging have greatly negated the positive impact of expansion of irrigation. Increased genetic vulnerability, incidences of pests and diseases, excessive application of agrochemicals, and environmental pollution are other serious adverse impacts and have aggravated the unsustainability problem. Biotechnology is one particularly promising way to improve agricultural productivity, and the private sector has played a major role in this area. Genetically modified organisms, or GMO crops have received quite a large amount of publicity, and farmer adoption of GMO crops has grown extremely rapidly over the past decade in some countries. Most of this growth has occurred outside Asia, but BT cotton has proved to be a favorite with farmers in China and India, and adoption has been exceedingly rapid. Insecticide use on cotton has traditionally been very high, so this innovation has reduced insecticide levels substantially, contributed to improved human health and a cleaner environment, and raised farmers' profits. This is truly a major achievement, although it will be a challenge to manage the development of insect resistance. Modern biotechnology has the potential to speed up the development and deployment of improved crops and animals. Marker-assisted selection, for instance, increases the efficiency of conventional plant breeding by allowing rapid, laboratory-based analysis of thousands of individuals without the need to grow plants to maturity in the field. The techniques of tissue culture allow the rapid multiplication of clean planting materials of vegetatively propagated species for distribution to farmers. Genetic engineering or modification, manipulating an organism's genome by introducing or eliminating specific genes, helps transfer desired traits between plants more quickly and accurately than is possible in conventional breeding. However, the spread so far is geographically very limited. Just 4 countries account for 99% of the global GM crop area. The United States with 35.7 million HA, Argentina with 11.8 million HA, Canada with 3.2 million HA, and China with 1.5 million HA. The number and type of crops and applications involved is also limited. 2/3 of the GM area is planted to herbicide-tolerant crops. All commercially grown GM crops are currently either non-food crops, that is cotton, or are heavily used in animal feeds, that is soybean and maize. Integrated pest management. The goal of IPM is to avoid or reduce yield losses by pests while minimizing the negative impacts of pest control. The term IPM was originally used to describe an approach to pest control with the primary aim of reducing the excessive use of pesticides while achieving zero pest incidents. The concept has broadened over time. Today, IPM can best be described as a decision-making and action-oriented process that applies the most appropriate pest control methods and strategy to each situation. To ensure the success of this process, the presence of density of pests and their predators and the degree of pest damage are systematically monitored. No action is taken as long as the level of pest population is expected to remain within specified limits. IPM promotes primarily biological, cultural, and physical pest management techniques and uses chemical ones only when essential. Naturally occurring biological control is encouraged, for example, through the use of alternate plant species or varieties that resist pests, as is the adoption of land management, fertilization, and irrigation practices that reduce pest problems. If pesticides are to be used, those with the lowest toxicity to humans and non-target organisms should be the primary option. Precise timing and application of pesticides are essential. Broad-spectrum pesticides are used only as a last resort when careful monitoring indicates they are needed according to pre-established guidelines. This broader focus, in which Judicious fertilizer use is also receiving attention, is also referred to as Integrated Production and Pest Management or IPPM. Experience shows that IPM has economic and other benefits for farmers and farm households. However, national policy frameworks in many developing countries have tended to strongly favor pesticide use through subsidies that distorted prices. Because of this, alternative pest control measures, even though successful technically, are often not financially competitive and farmers are reluctant to adopt them. In addition, generally weak extension services lack the capacity for the intensity educational programs needed to familiarize and train farmers in the use of IPM practices. In spite of these problems, IPM has been introduced successfully in many countries and for many different crops such as rice, cotton, and vegetables. In Cuba, IPM has been integrated successfully into organic farming. Where farmers have had no previous access to chemical pesticides, the introduction of plant protection based on IPM is a preferred option to avoid financially and environmentally costly overdependence on pesticides. IPM applied to rice has shown good to dramatic improvements in production, in some cases simultaneously reducing costs. Human capacities and networks developed for rice will continue to provide support for new initiatives. Combined with the proven successes, they will promote the introduction of IPM in other crops or cropping systems, particularly vegetables and cotton. Unfortunately, a quantitative evaluation of the uptake in terms of hectares covered and reduced pesticide use is only available for a few projects, making a global or regional estimate of its present and future use impossible. No-till or conservation agriculture. By far, the largest extent of agricultural land continues to be ploughed, harrowed, or hoed before every crop. These conventional tillage practices aim to destroy weeds and loosen the topsoil to facilitate water infiltration and crop establishment. In response to the problem, no-till or conservation agriculture has been developed. NT or CA maintains and improves crop yields and resilience against drought and other hazards, while at the same time protecting and stimulating the biological functioning of the soil. Various terms are used for variants of NT or CA in different countries, depending on the perceived importance of one or another aspect of the approach: zero tillage, minimum or low tillage, direct planting in straw, permanent direct seeding, and conservation tillage. The essential features of NT or CA are: A. Minimal soil disturbance restricted to planting and drilling, maintenance of a permanent cover of live or dead vegetal material on the soil surface. B. Direct sowing, crop rotation, combining different plant families, example, cereals and legumes. C. Adequate biomass generation, and D. Continuous cropland use. In some countries, the above-mentioned systems might lack some essential features of NT or CA and will therefore not have the same beneficial effects. Soil cover is needed to protect the soil from the impact of rainfall, which would destroy the porosity of the soil surface, leading to runoff and erosion. Crops are seeded or planted through this cover with special equipment or in narrow cleared strips. Direct planting or seeding is linked with NT or CA, since any more general tillage would bury most or all of the vegetable cover. After the first couple of years of NT or CA on a field, the stock of viable weed seeds near the soil surface usually declines, often to the point where weed incidence becomes minor with remnant populations at scattered spots in the field. In the first few years, however, herbicides may still need to be applied. Systems without continuous soil cover or crop rotation may not even reduce the incidence of weed in the long term. Example, wheat monoculture in the United States. After a number of years, yields have often risen to some 20 to 50% higher than what they were before under conventional procedures. The yields also become less variable from year to year. Labor costs can be significantly lower and labor demand is distributed much more evenly over the year. Input costs are lower as well, particularly for machinery once the initial investments have been made. In mechanized farming, less fuel is needed and smaller tractors can be used or fewer draft animals are needed for a given area. In areas without these power sources, the heavy manual work preparatory to crop establishment is drastically reduced. The spread of NT or CA approaches in the next 3 decades is expected to be considerable, but expansion will, for several reasons, vary widely across countries. It can take years before the new production system is widely known, understood, and appreciated. A further 10 years might be needed for its practical application over a large part of the country or a major farming system area. Agricultural technology in India. India's record of progress in agriculture over the past 4 decades has been quite impressive. The agriculture sector has been successful in keeping pace with rising demand for food. The success of India's agriculture is attributed to a series of steps that led to availability of farm technologies which brought out dramatic increases in productivity in 70s and 80s, often described as a Green Revolution era. The major sources of agricultural growth during this period were the spread of modern crop varieties, intensification of input use, and investments leading to expansion in the irrigated area. India spends 0.26% of the agricultural GDP on research and 90% of expenditure on R&D comes from the public sector. Alum 2004. However, R&D has paid little attention to crops grown under dry land conditions. Agricultural research and extension services need rehabilitation with a focus on subsistence crops and dry land agriculture. Krishi Vigyan Kendras (KVKs) need to be further integrated with state and district level extension mechanisms, and selected agricultural universities and research laboratories need to focus research on high-yielding hybrid coarse grains, pulses, and items for mass consumption. The ICAR has played a pioneering role in ushering Green Revolution and subsequent developments in agriculture in India through its research and technology development that has enabled the country to increase the production of food grains by 4 times, horticultural crops by 6 times, fish by 9 times, that is, marine by 5 times, and inland 17 times, milk 6 times, and eggs 27 times since 1950-51, thus making a visible impact on the national food and nutritional security. Thrust areas: streamlining transfer of ICAR knowledge and technology products through commercial, cooperative, and open public routes. Joint intellectual property management support in collaborative projects. Facilitation and advisories in techno-regulatory and policy matters related to intellectual property and technology management. Public-private partnerships in technology or know-how transfer and R&D. Improvements in yield necessarily require better technologies. However, proper mechanisms for making technology accessible to a wide spectrum of potential users are essential for benefits to be realized. In the case of India, the success of the Green Revolution was based on precisely this aspect. However, a further spread was limited due to the inability of the government to develop and disseminate newer technologies and complementary inputs over a larger geographical area, sets of commodities and classes of farmers. Significant yield improvements have not continued. Developments in molecular biology, biotechnology, nanotechnology, information technology, and geospatial technology are expected to provide significant new opportunities for productivity enhancement. These developments are also posing new challenges of capacity building and human resource development. There is a need to develop organizational policy and guidelines aimed at enhancing inventions and accelerating innovations in agriculture to harness opportunities by integrating modern and conventional research approaches. The Council is a custodian of huge ex situ collection of genetic stocks of crops, animals, fishes, insects, and microbes and would facilitate their sustainable use in genetic improvement of agricultural commodities over time and space through conventional and frontier scientific techniques.
For years, scientific and technological advancements have benefited farmers in the industrialized world by driving agriculture production. Modern agricultural technology allows a small number of people to grow vast quantities of food and fiber in a shortest period of time. The success of India's agriculture is attributed to a series of steps that led to availability of farm technologies, which brought about dramatic increases in productivity in 70s and 80s, often described as the Green Revolution era.